We already saw this graph previously, but it's important enough we need to come back to it and look at it again. When reactants are turning into products, and when we're thinking about the collision theory and those banging together, in terms of elementary steps, we are breaking and making bonds. And we will continue to emphasize this in multiple units, in our thermochemistry unit, in thermodynamics, in bonding. But breaking bonds requires energy. Those things are already stuck together, and we have to use energy to rip them apart. Making bonds, or maybe better stated as allowing atoms to bond, releases energy. So each part of a mechanism and each elementary step is going to have some requiring and some releasing of energy, or some increasing in potential energy and some decreasing in potential energy. When we graph that, whether it's for an individual elementary step or the overall reaction, we're looking at that idea for those collisions and the motion as those particles are rearranged. And sometimes we make a transition state. This is different from an intermediate. This is that moment as the bonds are being broken and formed, not that intermediate that is made before we get to our final product. So we might have one or more than one activated complex in an overall reaction, but for each bond breaking event or each elementary step, we have a transition state. That energy difference between where we start and where we go at the peak is called the activation energy. To see that, to hear that, and to use that term a lot is important, because that's a vocabulary term we want to include in our explanations. There is a mathematical equation that shows a quantitative relationship between several variables, but the key ones to us are the temperature, the activation energy, and the rate constant K. The equation is called the Arrhenius Equation. It relates all of those things. And what it does is it accounts for how reactants approach that activation barrier, and accounts for orientation, collision frequency, and a lot of other factors that might make an activation energy really high or really low. We won't do any calculations with this, but we do want to understand or remember that K is related to the activation energy and K is related to the temperature as well. So when we change the temperature, we're changing K, but that's not necessarily changing the activation energy. They are independent variables of one another, both of which can change our K, which we know would impact our reaction rate. A lot of times we are looking simply at, from reactants to products, what is the energy change? From reactants to the most energy needed, what is the what energy required, or the activation energy? But when we get into mechanisms, we know that there are multiple changes occurring. When that happens, we would have a reaction energy profile with multiple hills. The beginning would be our reactants, and the end would still be our products. The top of each hill is an activated complex or transition state, and then the bottom of our middle hills is where we observe intermediates. That's an important thing to note. Once again, the transition state is different from an intermediate. The intermediate is the product of an elementary reaction that then keeps reacting. So if we had a lot of steps, like that nitrogen and hydrogen mechanism that we show, we would have lots of big or little hills along the way. If we are shown a multi-step reaction energy profile, it is a useful way of understanding how many steps would be in our reaction mechanism. Each hill and valley corresponds to a step. We have put energy in, and energy has come out for our collision or our bond breaking events. This would be a 1-2-step process right here. The intermediates are shown, activation energies for different things are shown, and an important piece is whichever uphill is the biggest requires the most energy and therefore has the highest activation energy, but is also the slowest step. This is a two-step mechanism with a slow first step and a fast second step. It doesn't take much energy to get from our intermediate to its transition state before turning into products. So we can turn mechanisms into graphs and graphs into mechanisms in valuable ways that show us about the fast and slow steps, that show us about how many steps, that help us think about our intermediates, but also maybe help us to envision some transition states that we pass through during that process.